Welcome to this explainer. Today we're going to trace the absolutely fascinating origins of the current AI boom. We'll uncover the true roots of the tech we're all using every single day, and, maybe more importantly, reveal a massive, glaring technological hurdle we still have to conquer. I mean, we hear constantly about artificial general intelligence, or AGI, right? But as we're about to discover, we are missing a huge, fundamental piece of the puzzle. So let's dive right in.
Okay, let's start with this striking reality from Andrew. He's a former Google Brain researcher who spent 14 years at the absolute frontier of AI. Despite all the incredible hype right now, the ultra-smart chatbots, the autonomous agents, the workflows doing our jobs for us, AI is still shockingly blind to the basic physical world around us. People constantly claim AGI is right around the corner. But really, how can we be there when the most powerful computers on Earth are fundamentally stumped by the visual reasoning of a typical preschooler?
To understand how we fix this, we'll walk through this roadmap. First, the modern Bell Labs. Second, the foundation of LLMs. Third, the AI vision gap. And finally, the next frontier.
Let's kick things off with Section 1, the modern Bell Labs.
So picture this. About a decade ago, you had this incredibly historic environment that essentially nurtured the brilliant minds responsible for defining the last 10 years of AI. Google Brain brought together incredible talent. We're talking heavy hitters like Jeff Dean, Ilya Sutskever, and researchers like Andrew, all in a highly specialized, really small team. And they operated under this profound core belief, championed by legends like Jeff Hinton, that we should actually model artificial intelligence after the human brain. The idea was simple, but at the time, totally radical. You don't try to design the perfect, rigid, rules-based network from scratch. Instead, you build these adaptable networks of artificial neurons, and just let massive amounts of data wire the connections together. It's basically mimicking how our own brains learn and function through raw experience.
Now, what's really wild is the unique cultural formula that allowed this innovation to happen without your standard corporate red tape. They were totally unapologetic about their incredibly low acceptance rate for their residency programs. They didn't just want perfect GPAs. They were looking for intense curiosity and highly unique backgrounds. But, and this is the kicker, once you were in the door, there was zero pressure to launch a product immediately. Literally zero. There was massive psychological safety. Researchers were completely comfortable showing early, flawed results or just flat out being wrong around their peers. It was this environment of pure, untethered research creativity where the only goal was just making a giant leap forward.
And because you had this intense talent density in one physical place, it led to incredible learning by osmosis. Just by sharing a micro kitchen or grabbing coffee in the corridors, researchers absorbed high-level problem-solving principles. They learned exactly when to push through a really frustrating roadblock and when to completely abandon a bad project, just by watching the elite leaders work. It vividly proves that physical, in-person collaboration sparks spontaneous ideas that, honestly, isolated remote work on a screen simply cannot replicate.
All right, moving on to Section 2, the foundation of LLMs.
So that culture of osmosis we just talked about, it directly sparked the tech we use today. Back in 2015, way before modern chatbots took over the world, Andrew and his colleague Claude wrote a foundational paper on pre-training and fine-tuning. They realized that training a model to simply predict text, which we call language modeling, gave it this incredibly broad baseline understanding of how the world works. They proved this by taking a generalized model that had just learned basic language patterns and fine-tuning it specifically to judge sentiment on Rotten Tomatoes movie reviews. And astoundingly, this pre-trained model absolutely crushed every single supervised classification method out there. It proved, without a doubt, that generalized learning was the master key to specific mastery.
If you ask experts what the core components of modern large language models actually are, they'll point right to this triangle. First, the transformer architecture, which was a breakthrough way for AI to pay attention to context and map the complex relationships between words over long distances. Second, the language modeling objective they discovered back in 2015. And third, the sheer ability to scale it all up by feeding in the entire web. The absolute beauty of this setup is that it's like a giant sponge. It can endlessly draw in unstructured data and effectively utilize it, constantly self-improving without needing humans to hold its hand.
From that 2015 paper, the technology evolved rapidly. It started pretty quietly in the background, with convenient, small-scale features. Stuff you probably use every day, like Smart Compose and Smart Reply in your email. But researchers quickly noticed something unbelievable. As they scaled these models up, throwing vastly more data and computing power at them, the framework just kept working. It never broke down. This relentless scaling through models like GPT-3 and Gemini, combined with new tweaks like instruction tuning to make them actually helpful to talk to, led us directly to the wildly advanced text capabilities dominating our daily lives right now.
Which brings us to Section 3, the AI vision gap. But despite this explosive progression in text, we have hit a severe paradox. When we look at text and coding tasks, AI is basically operating in the modern smartphone era. It's the newest iPhone. It writes advanced code logic and does high-level math instantly. But when we look at visual problem solving, our AI is lagging decades behind. Actually, it's basically stuck in the era of those chunky brick phones with the pull-out antennas. Think the old Nokia 3310. Visual AI operates at an incredibly pixelated 64 by 64 resolution on standard benchmarks. Sure, it can recognize a car in a photo, but honestly, that's kind of where its usefulness ends. The specific failures are actually staggering when you look at the baby vision benchmarks. I mean, how can multi-billion-dollar models consistently fail at tasks a kindergartner finds totally trivial? They can't accurately count the number of glasses sitting on a table. They completely fail at simple spatial board games that just require basic geometric logic. And most critically for the physical world, they are completely unable to look at a simple 2D diagram and trace where two basic wires connect. It is just mind-boggling to think that an AI capable of writing advanced software architecture is entirely fundamentally blind to basic physical reality.
So how do we fix it? Let's hit Section 4, the next frontier.
This massive gap in capabilities is exactly why the landscape of AI development is shifting so drastically right now. We're seeing top-tier talent leave the ultimate safety of massive tech conglomerates to pioneer this next major leap totally independently. Because, let's face it, within big tech, the path upward often turns into navigating bureaucracy and corporate politics rather than executing pure research. But remembering those early days of Google Brain, when pioneers believed that success was a guarantee if you just followed the data, researchers are stepping out to take ownership of their own destinies. Independent frontier labs, like Lorian, are being built specifically to escape that corporate politics and focus 100% on giving AI true sight, aiming to conquer visual AGI once and for all.
So, why does this matter so much? Well, solving visual AGI isn't just about making a slightly smarter chatbot. It's the absolute key to transforming our physical world. Right now, major enterprises make minimal use of AI because their highest value work is fundamentally physical and spatial. You can't just use a text prompt to reliably design a brand new aerodynamically sound aircraft engine. You can't use math equations alone to map the intricate physical wiring of a massive new data center. Visual AGI is the ultimate bottleneck. Until AI can accurately see, measure, and understand 3D space, it's going to be held back from sparking the next revolution in engineering, architecture, and global infrastructure.
And that leaves us with a truly massive concept to ponder. Andrew mentioned drawing inspiration from Isaac Asimov's Foundation series, which is this legendary sci-fi story all about planning not just for decades, but for thousands of years. Consider this. If we successfully conquer this vision gap, giving AI the ability to perfectly see, engineer, and build our physical reality, how will mastering visual AGI today fundamentally rewrite the distant future of our entire civilization? Thank you so much for joining me for this explainer. Keep asking big questions, and I'll catch you in the next one.